Calculus, video 81, the area of a region with respect to y. Okay, so before we talk about the area of a region with respect to y, let's talk about the one we did previously, which was the area of a region with respect to x, so we can compare the two. Okay, the area of a region with respect to x, in this case, that's the ones we've done so far. We had two functions, f and g, and in this case, the one I've drawn here, the f ends up being the top function, the g ends up being the bottom function on the interval between a and b. Right, that flips after that, but for a to b, f is the top function, g is the bottom function. We're looking for the area of the region. Note that the bounds are the intersection points, and they are x bounds. These are a and b on the x-axis. The area ends up being the integral from a to b x bounds of the top function minus the bottom function, and notice that it is a dx here. To find the area of a region with respect to y, you often have a little bit different setup. Your curves might end up looking a little bit different. So maybe you have a curve, and maybe I'll just use a straight line here. Let's call that f of x. Actually, it may not be f of x. It could be f of y. Let me just draw the curve for a second. And the second curve might look something like this. Okay. Now you have a region here. And the reason why integrating with respect to y here, finding the area of the region with respect to y here, is because if you try to do top function minus bottom function and in x bounds, you get something kind of weird. Okay, so think about top minus bottom, and then we'll go with respect to y. If we try to do top minus bottom, you get your left bound here, a, and the top curve is the one in blue. The bottom curve is the one in green. And that's all fine until you get to, say, this point. Let's call that B. After that point, something kind of weird happens. The top curve of the region is no longer the line. The top curve is this portion of the green curve. And the bottom curve is this portion of the green curve. You have like two portions of that green curve on the interval from B all the way to C here. The top function is the green curve, and the bottom function is the green curve. It's probably going to end up being like, where the top function is, say, square root of x minus 2, and the bottom function is negative square root of x minus 2, or something like that, right? Where one is a positive version, and the other one is a negative version. But it just ends up complicating things because I have different top functions than bottom functions midway through here. So we don't do that. Well, we can. We're not doing it, but a better way, perhaps, exists. Let's see if I can erase this thing without deleting my actual curves. Okay. So instead of trying to force this to be top function minus bottom function, what we could do instead is right function minus left function. Because the right function is this the whole time. That is always to the right, and the left function is always, say, here. So instead of doing top function minus bottom function, where I have to kind of split my region into two different regions depending on what's on top and what's on bottom, we can do right function minus left function. And when we do that, we don't have x bounds anymore. When we do right function minus left function, the bounds are now here and here, A to B. They end up being y bounds. These are y bounds because they're on the y-axis. Y bounds here and here because they are on the y-axis. And so if we do right minus left, we have y bounds. We call that the area of the region with respect to y, using y bounds. And so often, these functions will be something like a function of y, f of y, and g of y. Meaning that when you write them out, you'll see them in like x is equal to 2y squared minus 4y, or x is equal to 7y. The function is in terms of y, as opposed to a function being in terms of x. Okay? So if you ever see this sort of situation, consider finding the area of the region with respect to y. For example, let's say we have determine the area of the region bounded by, and we have a couple of curves, bounded by x equals y squared minus 2, that's a curve, and x equals 4 plus y. Very good. This is kind of a giveaway that, hey, this might need to be finding the area in terms of y, because here I have equations in terms of y. X is equal to y squared minus 2. X is equal to 4 plus y. So I have equations in terms of y. So good chance I'm going to be using finding the area of this region with respect to y. Let's graph this. And we're often not as good graphing this direction where I have x's in terms of y. But basically, things are turned sideways. So instead of y equals x squared is a parabola that opens up. We have x equals y squared. That's a parabola, but now instead of opening up, it's going to open to the right. Okay? And the minus 2 means that we're going to be moving this thing left by 2. And one way, if you can plug, if y is 0, right, if y is 0, that means we're on the x-axis, and 0 minus 2 is negative 2. So if y is 0, x is negative 2. That means x is negative 2 and y is 0, x is negative 2 here. We basically get a, don't know what that was, we basically get a sideways parabola. This is x equals y squared minus 2. X equals 4 plus y is a line, because it's a degree 1. And so we have a line. If y is 0, x is 4. If y is 4, x is 8. That sort of a thing. If y is 0, x is 4. So we get this point here. If y is 4, x is 8. It's down the line. And we get, it's basically like a line y equals x. It's been moved to the right by 4. Let's use a different color here. Something like this. And maybe it's a poor drawing, maybe not, but we'll kind of see once we find the bounds. We have an intersection point here and an intersection point here. Once again, if you try to do top minus bottom, you have some kind of weirdness going on. The region is this region R. It's just where we're looking at this sort of area in here. So the farthest left, the top function would be this curve in blue, and the bottom function would be the curve in blue. Okay, that would be kind of weird. And then you have, that would work all the way until you hit this first orange dot. And then to the right of that, the top function is the blue curve, and the bottom function is the orange. Okay, that's fine, and we could make that work, but it's easier in this case to do right function minus left function, because the orange curve is always to the right, and the blue curve is always to the left in this particular region. So we're going to do right minus left, and we're going to then use y bounds. Okay, well, what are the bounds? So that's the first step. What are those y bounds? To do that, again, it's just the intersection points of those curves. So we're going to let y squared minus 2 equals 4 plus y. Where do those two equations intersect? Okay, now I have a y squared, a constant, and a y. That's going to be a quadratic, so let's move everything to one side. Y squared, subtract the y, minus 4 minus 6 equals 0. And then let's try to factor or use the quadratic formula. Thankfully, this one factors. Y minus 3 times y plus 2 equals 0. You can check that out. And the zero factor property says I can separate those and set them both equal to 0. And I get y equals 3 and y equals negative 2. Okay, that's a pretty poor drawing considering I didn't even get into the negative 2. So let me see if I can draw just a little bit better here. Should look more like, maybe erase a little bit more of these guys. Maybe more something like that. Too much. Trying to get rid of that orange dot, but it's not wanting to go away. We'll just leave it. Okay, so now my intersection points look like this. Again, still not the best drawing, but you get the point. Okay, so what we're saying here is on the y-axis, we have -2 to 3. And now that I'm looking at it, maybe my first drawing wasn't so bad after all, because I went from X to Y. Let me back that up. Okay, so the y bounds were up at 3, y equals 3, because we're on the y-axis, and y equals -2. Okay. So we're going to go, area is the right curve minus the left curve on the y bounds, everything in terms of y, so your equations are in terms of y, and we'll be integrating with respect to y. We'll have dy. And we get this. Area is equal to the integral from -2 to 3, these are y bounds, of the right curve, that's 4 plus y, minus the left curve, that's y squared minus 2, in parentheses. This is right minus left. And make sure you're doing dy here. I would go ahead and try and simplify this before we integrate. And so we have the integral from -2 to 3 of, I'll have -y squared, a positive y, and a 4 minus -2 would be a positive 6 dy. Integrating that, I get -1/3 y cubed plus 1/2 y squared plus 6y, evaluated from -2 to 3. Fundamental theorem of calculus says we get -1/3 times 3 cubed plus 1/2 times 3 squared plus 6 times 3 minus -1/3 times -2 cubed plus 1/2 times -2 squared plus 6 times -2. All right, let's see, that's 3 cubed 27, divided by 3 is 9. I get -9 plus 9 halves plus 18 minus -8, so positive 8 thirds. 4 would be plus 2, and then -12. 18 minus 9 is 9. 9 plus 4.5 would be about 13.5. And over here, 2 minus 12 is -10. -10 plus 8 thirds. Let's see, -10 would be -30 over 3. Plus 8 would be -22 over 3. So 13.5 plus 22 over 3. I'm getting about 20.83. So the area of the region, my region drawn here, possibly poorly drawn, is about 20.83. Pretty good. So that's how we use finding the area of a region with respect to y. Go ahead and put that down so we have it all in words here. Area of a region with respect to y. We have area is equal to the integral of a to b, where those are y bounds, right, on the y-axis, of the right function minus the left function dy. Or you might see it like this, the integral from a to b of f of y minus g of y, functions in terms of y, dy.